Welcome back. In today's lesson, we're going to finish drawing the upright, and we're going to cover the last of the theory that we need to cover for this introductory level lesson. The next step that we need to do is to put a tongue on the upright so that we can plug it into the base. And here we're going to make use of our philosophy that lazy is good. But before we get started, you can see that the shape looks like it's kind of flaring out visually. It's not actually flaring out. The back edge is actually the same length as the front edge. It just visually appears to be flaring out because we expect it to be a bit cone-shaped due to the perspective effect. If we want it to look a little more natural while we're working on it, we can select Perspective from our View Tools menu and we'll get that kind of coned-in shape that we would see in real life. If we want it even more realistic, we can add Shadows and Shaded mode from this same drop-down. We usually run without perspective, but sometimes you want it, and this isn't bad looking, so we'll leave the perspective switched on. To add the tongue, what surface are we going to draw on? By now, you should all correctly tell me that we're going to draw on the bottom of the upright. So select this surface, and then we'll turn it so that that surface is normal to our line of view. The tongue is going to stick out, so what type of 3D object is that? Yes, it's an extruded boss base. Because lazy is good, we're going to try to position this thing and set it to size with a minimum number of dimensions. We'll reach up and we'll get a center line, and we'll set the one end of that center line to the midpoint of one side of the upright, and then we'll go across horizontally and we'll set the other end of the center line to the midpoint of the other vertical. We'll press Escape to finish drawing that line. Is the line centered top to bottom? Well, the answer is yes, because we started on the midpoints of the end lines. So obviously it's centered along the lines that we'd set it to the midpoint of. Now remember when we talked about our entities and how they can be used to locate things or to grab something, right? One of the entities that we get on any straight line is a midpoint. So if we select the midpoint of our line, it's going to be centered side to side. We already know that the line is centered top to bottom. So the midpoint of that line is going to be the geographic center of this entire rectangle. That's good. Why is it good? Because it saves us work. Instead of using our usual corner rectangle, we can get a center rectangle from our rectangle drop-down this time. We can set the center of the rectangle right at the center of that surface and just drag it out. It's centered, and no matter what we do with the size of that surface, it's going to remain centered. If we used dimensions to position it, then when we change the size of the surface, we would also have to change those dimensions. This way we don't. Notice that I drew the rectangle much bigger and thicker than it needs to be. That's to make it easier to select the lines when I want to put dimensions on them. We're going to put dimensions on them to force it to size, and we're going to go with a horizontal dimension of 70, and we'll say yes to that. And we'll go to the vertical dimension. It's currently 9.94. We don't want that. We want 4.7, right? We don't need to design in any clearance here because the kerf of the laser will set an appropriate clearance for assembly. But if we were working on a 3D printer or a metal cutting machine, we would have to make the size of the hole larger than the size of the object that needs to fit into it, or we'd run into problems during assembly. So we've got an enclosed shape, and since all those other lines are construction type lines, they'll be ignored, and we don't have to worry about them when we extrude. The solid lines make a nice closed contour. So we're going to say yes, and we're going to exit sketch. Now this shape is sticking out 10 millimeters, which is not actually that bad in terms of design, but we are kind of stuck because we're laser cutting, and this tongue is going to intersect with a base that's 2 layers of 4.7 millimeter plywood thick. Because I'm lazy and I don't trust my own math, I'm going to type in 4.7 times 2. Boom! That's a 9.4 millimeter tongue, which is exactly what we wanted. We'll say yes to accept our changes. So now we've got our tongue, but if you look in this corner, there's a potential problem. If we try to plug it into a groove the exact same size, because this is a sharp corner, we're going to have to get it lined up absolutely perfectly to put it into the groove. But if we have a little bit of a slope on there, then that slope will allow us to be a little bit misaligned and yet still help that part slide right in. Now the angle of the slope, we're going to talk about that in a minute. The first thing we need to do is say OK to the chamfer tool and select the edges we want to chamfer. Then we select this edge. Oops, I got a face there instead of an edge. So I'll just go up to the box and I'll right-click on the face and I'll press Delete. Try again, and there we go. It defaulted to a 10 millimeter 45 degree chamfer. You can see that that's not going to really do us much good because the chamfer is so big that it would allow the top part to move side to side pretty good because there's no adjacent walls normal to that vector to hold it into place. So obviously that's way too big. I think 2 millimeters is more reasonable. And that's pretty good. It's still at 45 degrees though. So we'll take a little tiny theory break here and we'll talk about how these angles work. Think of this a little bit like a doorstop, a wedge shape with a rise over a run. But right now it's at 45 degrees. The rise and run are identical. So if we come in misaligned and the slope hits this corner, it's going to create a force back upwards equal to the side-to-side force that's being generated. So this impact is going to be just as likely to bounce the part back out of the slot as it is to redirect the force to move it side to side so it can fall in properly. If we go flatter than 45 degrees, say 30 degrees, then we're actually going to get more force back upwards than we are side to side because the amount of force generated is inversely proportional to the angle between the force vector and the slope. But if we go to, say, a 60-degree angle, then it'll give us around 1 unit of vertical chamfer for every 2 units of horizontal chamfer. This puts the mechanical advantage in the right direction. We'll try this on our part. So now we've got an alignment allowance of plus or minus 1 millimeter, which gives us a bit of room to play with. But now the side-to-side force that the slope will create is much greater than the force back upwards, so it will easily move the upright side to side so it lines itself up and drops in. Plus, unlike the 10 millimeter chamfer we started with, it still has 7.4 millimeters of vertical wall contacting the inner wall of the slot in the base. So you can see that we can change the angle. We can even go distance as well as by angle. We're going to try 2 and 10. Let's have a look and see what that looks like. Yeah, that looks kind of silly. So let's try 2 vertical, 1 horizontal. That's pretty good. It's pretty close to our 30-60 that we like. Or if we wanted to, we could use angle distance to set a similar result. So that's a pretty good chamfer. We'll say yes, and we'll click. That's almost the entire part. We've drawn everything, but now it's time to learn a little bit about how the CAD operates and how it draws. Let's get started on that. I'd like you to take your zoom window, zoom in on one of the filleted corners and zoom in pretty close. You can see that your lines here aren't exactly smooth. They're kind of herky-jerky, aren't they? So what's that all about? Well, we're going to take a bit of a theory break and we're going to talk about it. If I draw a circle and I want to know the area of that circle, and all I've got with me is a ruler that can measure straight lines, can I make a pretty good estimate of the area of that circle? Well, the answer is yes, I can. I can measure it in a few different directions and find the midpoint pretty accurately. If I then take an isosceles triangle where the base of the triangle is a line of best fit with the outside diameter of that circle, and the tip of the triangle is on the midpoint of the circle, what's the area of that triangle? And of course, the answer is the area of a triangle is always 1/2 base times height. If I then draw a bunch of identical triangles and completely fill the circle with these identical triangles, what is an estimate of the area of that circle? Well, of course, the estimate is the sum of the areas of those triangles. N times base times height, all divided by 2. So let's have a look at this. Where is our error of estimate coming from? Well, the vertex of every triangle is in the exact same spot in the center of that circle, so there's no error there. The side of each triangle mates up perfectly with the side of the next triangle, so there's no error there. So the error is between the line of best fit of the base of the triangle and the curve of the circle. Why is this? If we want to do an analogy here, we can say let's take a 1-foot ruler and we'll put it on a basketball. So we've got this 1 foot of straight line and it covers the arc of a basketball for 1 linear foot. If you were to put a 1-foot ruler right up against a basketball, would there be air gaps between the end of the ruler and the basketball? The answer is, of course, there's going to be a big air gap between the ends of the ruler and the basketball. If we then take the same ruler on the surface of our perfectly spherical Earth, and we put the ruler up against the surface of the Earth, we would be hard-pressed to see any light under the edges of the ruler at all, wouldn't we? That's because the curvature of the Earth over 1 foot is so little that it's almost straight across that line. 1 linear foot on a circumference that big covers very, very few radians of the arc. But when you put the same length of straight edge up against a much smaller diameter arc, then you're going to cover a lot more radians in that linear distance, and the divergence between a straight line and an equal length of arc is going to be much greater. So how can we use this principle to make our estimate of the area of this fixed size circle much more accurate? Well, if we take the number of triangles and we double it, then each of those straight lines covers half as many radians of the arc, doesn't it? Therefore, our error of estimate drops to half. If we double the number again, we have the error yet again, and so on and so forth. If we took an infinite number of triangles and we filled the circle with this infinite number of triangles, what would our error be? Well, of course, we can't actually do an infinite number of triangles, but the error at infinity would be 0 if we could. When we ran into this infinity problem back in high school, we'd use limits to get around it. So, the area of this circle is the limit as n approaches infinity of nbh over 2. Now suddenly we remember that the area of a circle is pi r squared. Doing some substitutions, that means that the limit as n approaches infinity of nbh over 2 is also equal to pi r squared. This means that pi is equal to the limit as n approaches infinity of nbh over 2 r squared. We've just done a mathematical proof of pi, and we could actually do a really accurate estimate of pi by using this equation and physically measuring these things out. So here ends our little side trip into theory land. Why did we talk about this? Because SolidWorks does not actually use curves, ever. Curved lines are always a series of straight lines that estimate the curve. When these polygons get changed into 3D features, this means that the entire feature is made up of a series of 3D polygons with straight line edges. If you remember that rectangle sketch back in lesson 1, we made it into a polygon by changing the opposite sides so that they were no longer the same length. Then we calculated the length of the base using trigonometry. With the top line held to a fixed length by its dimension, the length of the base would vary depending on the angle of that top line, the hypotenuse. Well, similarly, if I hold up a piece of paper with a 10 centimeter square drawn on it so that you're looking normal to the face of the paper, the square will look like a square. But if I tilt the paper back on the horizontal axis, that square is going to start to appear shorter and shorter in height while remaining the same width. Just like happened in lesson 1, the apparent length of that line that's tilted back, when displayed on the screen that's normal to our line of vision, will be cos theta h, where h was the original height of the line, and theta is the angle it's tilted back on relative to the display screen. Now that math is a pain in the backside, but the reason that we talk about it is that every single time you take your mouse or the cube and you reorient this part, for each and every one of the thousands of polygons in the part, this math needs to be done by the CPU and the GPU. The apparent smoothness of those arcs is based on the number of parts that it's broken up into, the number of little line segments. So even in standard resolution, you can see that there would be an awful lot of triangles and rectangles to do these calculations for. What that means is that a CAD uses a lot of processor time and an awful lot of video processor time, which is why any powerful CAD always requires a very powerful computer. But it also means that if you've got a really complex shape with a lot of geometry to it, it's going to really load down your system, and it may cause delays while it does these calculations. So to speed up the CAD defaults to a fairly low resolution. Like most things in making, this solves one problem, but then it causes another. If we leave things in low resolution, the lower resolution we're running in carries over into the actual part when we export it for 3D printing or laser cutting. We can turn up the resolution on the export engine, but that just means we get a crisper, cleaner, herky-jerky curve. So how do we fix this? Well, we can go up here and we can select this sprocket-looking thing. System Options. We can go to General System Options, and then we're going to open the Document Properties tab, and we're going to go down to Image Quality. We can see the slider for image quality. If we slide it all the way to the left and look at the circle in the preview, we can see the circle is estimated by 6 triangles. As we go the other way, it gets smoother and smoother. So we'll put the slider right up into the red. For something this simple, because we have a pretty powerful computer, this won't slow it down one bit. The wireframe resolution, well, it doesn't preview, but we'll slide into the red as well so that no matter what we're doing with this shape, it will be rendered in high resolution. We'll exit that menu and we'll zoom in the corner again, and now we've got a super smooth curve. Now the question is, how much more math do the processors have to do at a higher resolution? Well, we're working in 3 dimensions, so let's start by figuring out how much more math will be needed if we double the resolution. When we're going to double the resolution, we're going to double the amount of information that we know about each direction, correct? So we've got twice as much information about x, twice as much information about y, and twice as much information about z. So the answer is 2 times 2 times 2. The amount of math varies with the cube of the ratio of the change in resolution. So if we double the resolution, it has to do 8 times the math. If we quadruple it, 64 times the number of calculations will be needed. So typical to any kind of engineering, there's a trade-off to be made. But what we do to get the best performance in both the drawing mode and the export mode is we leave the drawing in the lower default resolution while we're drawing it, and then just prior to export, once we're done all the drawing operations, that's when we put the resolution up. We don't have very many more drawing operations to do on our parts, so we'll just leave the resolution up because it looks really nice this way. So that's all we need to do on the tombstone upright, but we can do a little bit of fine tuning on the color because I'm sick of looking at gray. Let's go up here to the top of our directory tree and let's select Teaching Document Lesson 1. This is the master control for this part. Everything below it in the directory tree is part of Teaching Document Lesson 1. Every command we apply at this level is going to be a global command and will be painted onto everything else below it. But it will be a global command with a caveat. If we input a global command for a new color, for example, it's going to paint everything that isn't already some other color into the color we've selected. But a color instruction on one of those specific features down below will override the global command and keep the old color if it pre-existed the global command. And it will overwrite the global command if the global color was selected first. But the global command will paint everything else, so we're going to go up here, we're going to right-click, we're going to get our beach ball, we're going to select Teaching Document 1 because that's what we want to apply to, and we're going to paint this part a lovely lime green. So we're done the upright, and we'll say Save. Well, that's it for now. We'll design our base and we'll assemble the upright and the base in Lesson 2i. See you soon!